Good morning. Welcome to session 5 of Unit 4 in learning the course Computer Organization and Architecture. In our previous sessions, we discussed about memory hierarchy, main memory, associative memory, cache memory. Now, in today's session, we are going to discuss about virtual memory. The main objectives of this session are to know what is virtual memory, to understand the memory mapping in virtual memory. The main outcomes of this session are, by following this session, the student will be able to understand the address mapping in virtual memory and also able to learn what is virtual memory. So now, before going to know the address mapping of virtual memory, first we need to know what is virtual memory, what is the importance of virtual memory, that we need to know. So, programs and data are first stored in auxiliary memory. So, initially whenever you written a program or you entered any data, that is stored in auxiliary memory. Portions of the programs or data are brought into main memory as they are needed by the main memory. So, as they are needed by the CPU. So, not main memory. So, whenever the processor want to access the data or whenever the processor want to process any instruction, whenever the processor needs any instruction or data, that is brought from auxiliary memory to main memory. Virtual memory is a concept used in some large computer systems that permit the user to construct programs as though a large memory space available equal to the totality of auxiliary memory. So here, virtual memory is a concept which is used like auxiliary memory only, secondary memory only. Okay, so the programs and data are stored initially in virtual memory. So whenever the processor want to access those programs or data, that is brought from virtual memory to main memory. Okay. Now, each address that is referenced by the CPU goes through an address mapping from the so-called virtual address to a physical address in main memory. So whenever the CPU want to access the data, the virtual address is different from main memory address. Virtual memory is a larger when compared to that of the main memory. So, if the main memory contains some number of locations, the number of bits required for the representation of address of these locations is different from the address of virtual locations. So, that's why there should be a mapping from the virtual memory address to main memory address. So, an address used by a programmer will be called as a virtual address. So, what the programmer uses? So, the programmer uses the address of virtual memory. The set of such addresses is called as address space. The set of virtual memory addresses is called as address space. An address in main memory is called as a location or physical address. The set of such locations is called as memory space. So, the address used by the programmer is virtual address. Set of virtual addresses is called as address space. The address of main memory is called as physical address and set of physical addresses is called as memory space. Next. For example, for explaining about that virtual memory and main memory clearly, here we are taking two examples. Let us see those two examples. This is the auxiliary memory. This is the auxiliary memory and this is the main memory. So, the auxiliary memory, initially the program 1, data 1, data 1, program 2, data 2, 1 corresponding, that is the data corresponding to this program. The data corresponding to this program. So, they are stored in auxiliary memory. So, here if it contains 1024k locations, it contains 1024k locations. 1024 means 2 power 10 locations. Again 1k means 1024. That is 2 power 10. 2 power 10 into 2 power 10 means 2 power 20 locations are there. For the representation of address of each location, it needs 20 bits. For the representation of address of each location, it needs 20 bits. Now, this is the main memory. So, whenever the processor want to execute the programs or it want to access any data, those portions of the programs or data are transferred from auxiliary memory or virtual memory to main memory. Suppose if it wants program 1 and data 1, Now program 1 and data 11 are copied to here. This is main memory space or memory space. This is the address space and this is a memory space. It is having 32K locations. 32K means 32 into 1024 locations, which is having 2 power 15 locations. So for the representation of address of each location, it needs 15 bits. It needs 15 bits. But the CPU cannot communicate directly with the virtual memory. It has to communicate with the main memory only. The CPU knows only 15-bit address, but the programmer writes the program with 20-bit address. Now, for accessing the programs by using this 15-bit address, there should be an address mapping from auxiliary memory, that is virtual memory to main memory, that we are going to explain, right? Now, what the example we said, we need 20 bits for physical address, 20 bits for the virtual address and 15 bits for the physical address. Now, the CPU will reference data and instructions with a 20-bit address, but the information at this address must be taken to physical memory. So, there should be a mapping from virtual address to physical address. Now, how the mapping is to be done? This indicates a mapping table from virtual address to physical address, a mapping table. Now, let us see. Here we have virtual address register that is having 20 bits. Here this is the mapping table. So, we pass this virtual address to the mapping table, and here this is the memory table buffer register. So, it goes for identifying where the mapping is occurred, from which location of virtual address to, from which location of physical address, from which location to which location the mapping will occur, that will be represented by the memory mapping buffer table. This is the memory address register, that is the main memory address register, and this is main memory, and this is main memory buffer register. So, this entirely indicates the mapping, memory mapping table for a virtual address. So, this will be clearly explained by considering the pages and blocks. Now, what about the pages? What about the blocks? So, that is we are going to divide the virtual memory and main memory into various parts. Based on those parts, we are going to map the virtual address to main memory address. Now, this table implementation can be simplified by considering the address space and memory space each divided into groups of fixed size. Now, the physical memory is broken down into groups of equal size, which are called as blocks. That is, your main memory is divided into equal sized groups, which are called as blocks. Your virtual memory is divided into equal sized groups, which are called as programs. Now, the programs are also considered to be split into pages. Programs also stored based on the pages only. Okay, right. Now, for example, here we given your virtual memory, which contains 8K locations. These 8K locations are divided into 8 groups. Each group is called as a page 0 to page 7. Totally, it is divided into 8 groups. The size of virtual memory is 8K. So, it is divided into 8 groups. That is equal sized groups. So, that is each page contains how many locations? 1024 locations. That is 1K locations. This is having 1K locations. This is having 1K locations. And this is having 1K locations. And so on. This is having 1K locations. Totally, there are 8 1K locations are there. So, 8K is the size of this memory. Since it is 8K, it contains totally 2 power 13 locations. For the representation of address of each location, it needs 13 bits. And coming to main memory, it is having 4K locations. It is also divided into equal sized groups. So, here it is divided into 4 blocks. Those groups are called as blocks. Block 0, which contains 1K locations, block 1, 1K, block 2, 1K, and block 3, 1K. So, totally it is having 4K locations. That is, it is having 2 power 12 locations. For the representation of address of each location, it needs 12 bits. That is, we need to map the 13 bits virtual address to 12 bits physical address. So, how this mapping is done? Let us see. Now, here, this is the mapping table. What the memory mapping table that we explained, the same thing here I represented with the values. Okay. Now let us see virtual address here, which is having 13 bits. This 13-bit virtual address is divided into two parts. Okay, the first part is used for the representation of page number. Second part is used for the representation of line number. Since we have 8 pages, for the representation of page number, we need 3 bits only. So that's why page number contains 3 bits. The remaining, what the 10 bits that are present, that are used for the identification of line number. In which page, which line? For identification of line, we are using this address. Okay, right. This is the memory mapping table. This mapping table is divided into 2 parts. Okay, so this is also having, this table is having totally 8 locations. Those locations are represented from 000 to 111. That is, these locations are used for the representation of pages. This is page 0, page 1. That is, these pages are mapped to which block, that I need to know. So, that block number and corresponding presence bit. Okay. So, this presence bit, so if no block is mapped from any page, the corresponding presence bit becomes 0. But if any page is mapped to any block, so its corresponding bit becomes 1. So, that is, it is indicating page 1 is mapped to block 3. Its corresponding bit becomes 1. Page 2 is mapped to block 0. In the same way, these two also mapped. Now, suppose buffer register. So, this buffer register, I want to know this page is mapped to which block. It's okay. Since its corresponding bit is 1, it takes this value and this value is mapped with this one, main memory. So, if these two are same, then it goes for mapping with the line number and index line. So, that is the block, this page data will be stored in this block. Do you understand what I am saying? So, here I want to map page 1 to block 3. Okay, page, here this is page 0, page 1, page 2, 0, 1, 2, 3, 4, 5, 6, 7. So, I want to map page 1 to block 3, page 2 to block 0, page 5 to block 1, page 6 to block 2. Okay, that will be mapped. In the same way, line number also. In this line, what the data present in this line of that page, that data will be stored in the same address. So, since it is also having 1K locations, that is also having 1K locations. So, in the same way, so what the data which is present in page 5, the same data entirely will be stored in block 1. Block 1 lo, it will be stored, right? So, I hope that you all understood how mapping will be done, how the pages are transferred to blocks. So, how it will be done, you can understand from this mapping table, virtual memory mapping, right? So, I hope that you all understood the concept of virtual memory. So, I am going to recollect the things what we explained in this session. In this session, we discussed about what is virtual memory, what is the importance of virtual memory, what about the address space and what about the memory space and what about the pages and blocks and how to do mapping of virtual address to main memory address. Okay, based on pages and blocks. So, to assess yourself here, I given a question. Please answer this question. The question is, explain the memory mapping in virtual memory. In preparing this presentation, I used the digital content from various public sources. It is used only for educational purpose and not for the commercial purposes. Thank you for listening to the session. Thank you.